Okay. So since it's not clear to me whether I have time to do many things on Banach spaces, I will do some Hilbert spaces. And if we have time, I will come back to Banach spaces again. Okay. So this is what I plan to do now in Hilbert spaces. Once this is done, yeah. Once this is done, let me just minimize this. Yeah. Okay. Once this is done, we will come back to Banach. I mean, we have to do some Fourier analysis and other things. So I will concentrate on other things. And if we have time, I'll come back to Banach spaces. Okay. So I want to define what is called a Hilbert space. Before that, I want to define a sesquilinear form, then an inner product. Okay. So this is recording, I believe. Yeah. Okay. So we have a H be a linear space, okay, or a vector space. Then, so I mean, usually the inner product will look like this, but let me, for the time being, let me use a different notation. A function from H cross H to C is a sesquilinear form. It's not what is called a bilinear form. Bilinear, I mean, it's a function of two variables from H, two variables, I mean, H cross H. It's a function of two variables from H to C. So usually we have seen what is called linearity. If it is linear in both the variable, it's what is called bilinear. Here, this is not linear. It's not linear in both the variables. It's linear in the first variable. And antilinear.
Sir, sir, this H is just an arbitrary complex vector space.
Yes, is a linear space over C. Yeah. What else? It's a linear space over C. Okay.
Thank you.
Okay. You can take it over real, then you don't have to say this as linear form or something. It can be bilinear. We will be working with complex numbers unless it is specifically stated. Okay, it's called a sesquilinear form. It's linear in the first variable, antilinear in the second variable. Okay, that is if you have, if you take the xy and if you put alpha y, alpha beta, sorry, alpha beta y, then this will look like alpha beta bar xy. Okay, and it's linear. Of course, if you have x plus x1 plus x2 y, that is equal to x1 y plus x2y, like this. Similarly, xy1 plus y2, it will look like xy1 plus xy2. So sum you can take it out, and from it's only the difference is from the second variable you can take out a complex scalar as a bar. It's conjugate. So it's antilinear, or it's also called conjugate linear. This is something like, I mean, sesquilinear means it's 1.5 linear. That's what this says. What does 1.5 linear? It's one linear in the first variable. In the second variable, if it is real number, it's linear. So if it's not a real number, then you have to take the complex conjugate. So it's sesquilinear. This is what is called sesquilinear. So a sesquilinear form is said to be a seminorm. Okay. So now I will use a different notation. A sesquilinear form is a seminorm, semi-inner product, sorry, if one, if it satisfies this self-adjoint condition, bar. Okay, this is what is called self-adjoint. Okay. This is how you take the adjoint in a matrix. So it's similar to that. It's very related to that. In fact, you can form using inner product. You can form a matrix. If you take x1 up to xn, then you can form xi xj. That matrix will be self-adjoint. That's what this says. Okay. Though second condition is, in fact, it is positive. I mean, you can check this. You can take elements x1 up to xn. Then you can take a matrix xi xj. Okay, by taking inner product, it's a complex matrix. Then that matrix will be a positive matrix or a self-adjoint matrix. That's what these conditions say. So that's, we'll come to that later if needed. Positivity condition. Positivity condition is xx is greater than or equal to 0. So a sesquilinear form is a semi-inner product if it satisfies the self-adjoint condition and positive condition. So this is a semi-inner product, is an inner product if further, apart from satisfying self-adjointness and positivity condition, this xx equals 0 implies x equals 0. Okay. So then define if something is an inner product, then I mean, even if it is not an inner product, you can define a norm that will be a semi-norm. Okay. Define. So this will, there is no then. Define. We will prove it's a norm after proving Cauchy-Schwarz inequality. So norm x equal to inner product xx. Okay. So this is the norm associated with this. Okay. We will prove that this is a norm. So once we have proved, then we will call something as Hilbert space. I mean, we will prove it's a norm. So I should define only after that, but I am defining now itself. We will prove this is a norm. Okay. And H is a Hilbert space. If you have, it's called an inner product space. I mean, if you, any linear space with this is called an inner product space. This is called an inner product space. And it's a Hilbert space. It's called as an Hilbert space if complete with respect to that norm. Okay. Okay. So that we will come to that later. Okay. Now for the time being, so we will come to that. When we prove Cauchy-Schwarz inequality, we can prove. Before that, I want to make some important. So this I will give it as an assignment. I mean, this is very simple, but I want you to, all of you, to verify this once in your life. Okay, you shouldn't. So this is assignment. Verify, just verify. Verify the following. So this is true for any sesquilinear form. So if it is just a sesquilinear form, for a sesquilinear form, you verify this. So what is that you have to verify? Y equal to maybe 4xy equal to summation I power k x plus I power k y x plus I power k y. Okay. K equal to 0 to 3. I is the complex number I. Okay. K is a variable in the summation, and I is the complex number I. Okay. So you just have to use the linearity and other thing and you will get this. Okay. This is very easy verification, but it has to be done once. So that is why I'm giving it as an assignment. So this is one. And the second thing is this is also satisfied. So if H is over real, I mean, you don't need it to need other properties of the inner product like positivity, self-adjoint. It's only the linearity and conjugate linearity is enough for this. So we may use it later for some other sesquilinear form which does not give an inner product. So that's why I'm just mentioning that it's just a sesquilinear form. So if H is over real, H is over R, okay, H is a vector space over R, then we have something better equal to um, okay. So you don't, I mean, this is very easy, but you don't have to write it. Polarization. So this is only, I mean, since you are typing, you may take, in the writing is very easy. I mean, this is just, you have to write x plus y as inner product x plus y, inner x plus y, use the linearity, you will get it. So here I will get a 4. Usually this is 4 for complex numbers. You will not get this. This will be 4 real part of xy equal to x plus y minus x minus y square. That's what you will get. So only this is assignment, okay? Okay. So this is very easy. You just expand x plus y square. You will get that equal to norm x square plus norm y square. I mean, you write it like this, right? And that is equal to this. First norm x square, then norm y square, then xy plus yx. Sorry, this is for, so you need to be a real, sorry, this is not sesquilinear form. That is for sesquilinear form. This is for inner product. I'm sorry. This is for semi-norms or something. This is for a semi-inner product. We are using the conjugate property. No, this for reals is fine. Oh, sorry. Oh no, I changed it in the wrong place. Verify for this is for a, sorry, the assignment is for a sesquilinear form. Okay. So even if it is a real sesquilinear form, it satisfies this. That's okay. But for a complex sesquilinear form, I mean, if we, sorry, complex inner product, this is for a complex inner product. For a complex inner product, and this is a semi-inner product. Okay. What I mean, first, if you have a sesquilinear form, then this is satisfied. This is what is called polarization identity. Okay. We call it polarization identity. So if you have any sesquilinear form, then the polarization identity is satisfied, which I want you to verify. And for real Hilbert space, this is satisfied, which we can easily verify using this. It's clear from here. Okay. So if you have minus, you will get a minus here, and that minus will become plus here when you do, because you have a minus there, so it will become 4 in product xy, and the norms will cancel. Norm x square, norm y square will cancel. On the other hand, if it is complex, this is just going to be norm x square plus norm y square plus 2 of real part of xy, because this is equal to conjugate of that. Okay, so this is for complex numbers, it becomes like this. So that's why we get this. Okay. So in fact, if we have norm x square plus y square plus norm x minus y square, this implies norm x square plus norm y square. This is what is called parallelogram identity. Okay, which we have seen in geometry. So I mean, if you vary x plus y square, if norm x plus y square, you just expand it like this. So norm x minus y square, you expand it like this. Then the whatever the real part, 2 real part, that will cancel when you sum these two things. So you get norm x square plus norm y square. This is what parallelogram identity. So which has been verified now. Yeah.
Yeah, sir, can you just tell me the setting? Can you just repeat the setting of the part 2 that you mentioned here? If H is over R, then.
No. Let me clarify everything. Part one is if you have a sesquilinear form, that polarization identity is true. That's what I have said. Okay. If you have a polarization identity, if you have a sesquilinear form, for real inner product, this is true. Okay. For a sesquilinear form. When you have complex numbers, then you need a semi-inner product so that then this will satisfy. Okay. Because you are using the self-adjoinness, so you need a semi-inner product.
So
Okay.
in 2 it is again a sesquilinear form.
What?
So in 2 it is again a sesquilinear form.
Then you have to call, yeah, you are not using any other property, no, but you are using, I mean, you are saying something is a norm. You want that to be positive. Okay, let's call it inner product. Okay, I mean, you don't really use for semi-inner product, it's a sesquilinear form, but I'm calling it as norm, so I assume that it's a positive thing. So you have inner product. Okay, if you haven't, I mean, for sesquilinear form satisfies this, then you have to call this as you have to define this norm as the XX, the inner product XX. Okay, we are not using in this but we are only defining the norm like that. Okay, norm may not be positive if you have just a sesquilinear form. Okay, it's okay.
Sir, in the definition of sesquilinear form, we could potentially take two different vector spaces H and K, right?
Yeah, you can take.
So in the assignment, like, do we stick with the same vector space H or take H and K?
Okay, you stick with the same one. It doesn't really make it. No?
Okay.
Yeah. No, two different things. It does not make sense in this polarization identity because I'm using x plus I power k y, so which is in the same Hilbert space.
Oh yes. Yeah.
Okay, so that is only for the single Hilbert space. So what we have is the polarization identity. Then I give another assignment. This is assignment 2. Assignment 1 is polarization identity. Assignment 2 is prove the following. Prove. So if you have a norm, something on this, so prove that a norm on H arises from an inner product, comes from an inner product. If and only if it satisfies parallelogram identity.
Sir,
Yeah.
in the parallelogram identity, like should there be a 2 in the right hand
Yeah.
side? A 2.
Yeah. Yes. There should be some simpler way of writing parallelogram identity. Okay. Okay. We may not write it again, so it's okay. Okay. So the proof is simple. I mean, one way we have already verified. If it is an inner product, it satisfies parallelogram identity. If something satisfies parallelogram identity, then you use the polarization identity to define the inner product. You see, this is just a norm. What we have here is just a norm. So this is just a norm of x, norm square of x plus I power k y. Okay, if you have something, so using this norm, so that is why the polarization, the usefulness of polarization identity is you prove something for the norm, then you can use this polarization identity proof for the inner product. That's why this polarization identity is proved. That's why it's useful. So if we have a norm which satisfies parallelogram identity, then you define the inner product using this. I mean, inner product between x and y is 1 by 4 times this, which this right hand side. This right hand side can be defined using the norm. So then prove that using the parallelogram identity, prove that it's a inner product. That's all. It's actually an inner product. That's all. Okay, so that is an assignment 2. Okay, so these are very basic things. Now we come to something important. Now still I haven't proved it's a norm. So for that we need the following inequality. Cauchy-Schwarz inequality.
So your screen is not visible.
My skin is not visible. What happened?
Oh. It has become too thin. Yeah,
Now?
it's okay. Yeah, it's okay.
Now it's fine? Okay. Yeah, so something happened, it got moved. Okay. Cauchy-Schwarz. inequality. So this just says if you have x, something is an inner, though we basically need semi-inner product. Okay, so because later we may use it for semi-inner product, which may not be inner product, is an inner product, is a semi-inner product on H. Then you have already seen this for L2 spaces. This is the Holder's inequality. Holder's inequality is Minkowski inequality. Norm x by norm y. Okay, for all xy in H. Okay, so this is Cauchy-Schwarz inequality, and there is a converse of the Cauchy-Schwarz inequality. So that is the other way. Further, equal to this, the equality occurs. Then x and y are linearly dependent. That is, there exists a alpha in C such that x equal to alpha times y. Okay. Okay. Proof. Okay. So we want to prove Cauchy-Schwarz inequality. How do we prove that? So I mean, we want to use the positivity condition. Oh, this for the other way, it need to be a norm. I think it needs to be a norm. Further, if is an inner product, that Cauchy-Schwarz inequality is true for any semi-inner product. If there is an inner product, okay, then this is equal to this, and sorry. Then xy are linearly dependent. Okay, first we will prove the inequality for a semi-inner product. Okay. So we have a semi-inner product, but if it is a semi-inner product, this is anyway true. X plus alpha y for 2x and y in H. Okay. X plus alpha y square is greater than or equal to 0, of course. That is clear. Okay. But then this is equal to x plus alpha y, x plus alpha y. Okay. This is greater than or equal to 0. Now that is equal to norm x square plus yeah, 2 times real part of x times alpha y. So this alpha may come as alpha bar. Alpha bar xy plus norm alpha. Oh, I want to take this alpha to have modulus 1. Okay. Okay. Then for any alpha, I mean, this is true for everything, so I can take alpha in C with mod alpha equals 1. 1. So maybe I will take minus sign here. Okay. Well, we have chosen alpha norm 1. We can also choose, I further do something. I keep a t here. T be real. Okay. So there is t here. So I get a t square here. Then tx will come out as t here. Okay. This is some t. T isn't real. Okay. So for any t real, any alpha complex number with mod alpha equal to 1, this is true. Okay. Further choose alpha such that alpha bar xy equal to mod of xy. This is possible, of course, right? Xy is inner product xy is a complex number. You can choose some complex number to make it modulus, which is just
Sir, the right hand side of your screen is not visible properly.
Screen is not visible, right?
I mean, the right side, I mean, some letters are cut.
Letters are correct. What is cut? I mean, I haven't done anything here. In my iPad, everything is here. Why it's not there? I don't know. Should I do some? I mean, here suddenly it started not visible, or I haven't done anything.
And so, for example, at the top, like where we have written for all xy belonging to h, we can't see the h properly.
Here, you can't see the H properly.
And no, we can't see the h properly.
I don't know why. Let me try to pull it here once again. One second, something is happening. One second, I will remove this picture. It's not clear what I have to do. I'm just trying to move the window somewhere, but it's not moving. Now is it okay?
Now it's fine.
Now it's fine? Okay.
Yeah, now it's.
I just zoomed it. So it'll be okay. Okay. So yeah. So what I have done, I have just used the fact that some tx minus alpha x whole square norm square is greater than or equal to 0, where I have chosen the alpha to be of mod alpha equal to 1. And so, I mean, this xy is going to look like some mod xy times e power I. I mean, this is going to look like this times e power I theta. You take that e power I theta and multiply with that, and I mean, alpha to be e power I theta, then alpha bar is e power minus I theta. So this will become the mod. Okay, so this is clear. You can do this. Okay, choose alpha such that this happens. So these things imply 0 is greater than or equal to this real part will go away. That will become mod. Okay, t square norm x square minus 2t inner product xy. This mod plus norm mod y square. That's all. Okay. So this is a quadratic equation which is strictly greater than 0. So the roots has to be either both are equal, or it has to be complex roots. Okay. So this implies, since this should have complex roots. I mean, since this is greater than 0, if it is strictly greater than 0, it should have complex roots. So in particular, this will imply that whatever it's called, the discriminant is 0. Discriminant is less than 0. Okay, so b square minus 4ac, whatever in the quadratic equation, should be less than 0. So b square should be less than 4ac. So 4ac is that and less than this. So this implies here you have 4 times mod xy square is less than or equal to 4 times norm x square times norm y square. Okay. Okay, so we have proved Cauchy-Schwarz inequality. Okay. You can use other theorems of calculus to prove this also. Okay, this is one way of doing. Okay, now we want to prove the other way. So suppose equal to norm x norm y. Okay. Then whatever the equation we have, this equation, call this as star. Okay. Then star has equal roots. It has the roots and its equal roots. Okay. So there exists a T naught so that it is equal to 0. Okay, there exists T naught such that if you substitute T naught in the star, it is equal to 0. Okay, in that equation, it is 0. So that just implies, and alpha is also, you have chosen alpha also. So there exists alpha naught, T naught, alpha naught in C, T naught in real number, such that the original thing is 0. That is norm of Tx minus T naught x minus alpha naught y equals 0. This implies x equal to alpha naught. This implies they are linearly independent. That's enough. I don't want to say consider cases whether it is 0 or not. This implies x and y are linearly independent. Okay, it's clear. So we have proved the converse of Cauchy-Schwarz inequality. Okay, is this clear? Fine.
Yes.
Okay.
Yes,
Let me
yes.
go to the next one. I assume it's clear. So we have done polarization inequality, Cauchy-Schwarz inequality, parallelogram identity. Examples, we all know the car. We have been working with examples in Rn or Cn, Cn or Rn. Cn, in Rn you have real and not product. In Cn, if you have the x1 up to xn, y1 up to yn, summation xi yi bar. Okay. Summation xi yi bar. Incidentally, in physics, they usually have the first variable conjugate linear and the second variable as first variable is conjugate linear and the second variable to be linear. But in mathematics, we are doing this. Actually, physicists are right. Physicists are right. Because when we do few things, later when we generalize this theory, we need the linearity in the first variable and the conjugate linear in the second variable. But all mathematics books, it's linearity in the first variable, conjugate linear in the second variable. So we use that. Okay. On L2, we have this. On L2, if you have any sequence, so two sequence xn, yn, full sequence contained in L2, then inner product between xn and yn equal to summation xn yn bar. Okay. You know this exists, this will exist. Okay. And that's the usual Holder's inequality or whatever. Similarly, if we have on L2, if we have any fg in L2, then inner product between f and g. Okay. Okay, so these are all inner product which you can easily verify. It's linear, conjugate linear, and we have already, if integral mod f square is 0, then f is 0 almost everywhere, and that's what 0 element of L2 is. We are identifying L2 with respect with the equivalence relation that two functions are same if they are almost everywhere equal. So this gives a inner product. Okay, and in fact, every separable inner product will prove that will look like this L2. That we'll see later. So there are not too many inner product spaces. We will not deal with non-separable Hilbert spaces. Separable Hilbert spaces will look like this. Yeah. Okay. Okay. So what is the next thing? Okay. You can consider other things. There is something called Hardy spaces, which are also inner product space, where you consider holomorphic functions and with, so there are different things we can consider. And there are many, it's all many avatars of Hilbert space. It's you have many Hilbert spaces, but they will all look like L2 in a sense. They are isomorphic to L2. So all separable Hilbert spaces are isomorphic. That's what we will prove later. So there is no point in giving different examples. L2 is the canonical example. When it is separability, everything will look like L2. Small L2 or big L2, whatever. But you can have different, so you just it's the same thing which takes different avatar. Like there are, you can construct. Even within operators. For example, if you have operators on Hilbert space, we have considered operators on Banach space. We can consider operators on Hilbert space. There are Hilbert space contained in that. Okay, there is something called Hilbert-Smith operators, which I will deal in the next course. Okay. Hilbert-Smith operator. So this will form a Hilbert space with respect to some inner product. Okay. So this is what is called a non-commutative analog of the small L2. So, but still, all of them will be isomorphic to some L2. Okay. But still, this is just a different way of different presentation of the Hilbert space. That's all. Okay. We haven't proved. We'll prove that everything looks like L2 when it is separable. Okay. We'll come to that later. Okay, so these are examples. We will not spend much time on the example because there is only one Hilbert space. So next thing I want to prove is convex set. So we want to talk about something called orthogonality. Let's talk orthogonality. So definition. So the difference between Banach space and Hilbert space is in Hilbert space we have something called orthogonality. Using orthogonality, we can define something, a nice basis, which is called orthonormal basis. In Hilbert space, the bases are, in Banach space, the bases are not nice in the sense that we may not have a countable basis or something. Okay, you may have shorter basis, but something may not. Usually in infinite dimensional Banach space, the basis is always uncountable. Okay, the cardinality of the any basis is uncountable. That follows from Baer category theorem. But then we can have something called the shorter basis, which I defined. You take the span and take the closure. So the shorter basis can be countable, and there are nice bases for Hilbert spaces. So in that sense, Hilbert space is an correct infinite dimensional generalization of finite dimensional vector spaces. Okay, we have a nice inner product, and we can get orthonormal basis for something. So that's why we define orthogonality. There is no orthogonality, there is no right angle, there is no concept of angle. When you have the inner product is something which defines the concept of angle. For instance, you can define, if you have two vectors, x and y, okay, if you have x and y in H, then you can define the angle between them, cos theta, the angle between them as the, which is the inner product basically, norm x times norm y times cos theta equal to inner product x. Okay. Okay. So if the inner product is 0, then theta is 92. Say 90. Theta is 90. It's orthogonal. Okay. So we can define orthogonality. So we can define angle. In particular, we can define orthogonality like this definition. So we take xy in H. Xy is are orthogonal to each other if inner product xy equals 0, and we denote x is orthogonal to y. This is the notation for orthogonality. Okay. Okay. So if S is a subset of H, okay, then we take the orthogonal complement of S to be all those y in H such that xy equals 0 for all x in S. Okay. So this is what is called orthogonal complement. Which is of course not a set theory complement. This is what is called orthogonal complement. Okay. So we want to see the nice thing about orthogonality is if you have some subspace or if you have some set, then you can always, if the set is nice, a convex set, closed and convex set, then you can find from a point, you can have a point where which has a minimal distance from that. Okay. So this is something, so that is what is called the ortho, and that occurs with some orthogonality. That vector will be orthogonal to this. So that is the proposition we want to prove. Suppose C is a set. So we always assume H to be an inner product space. H is a Hilbert space. Okay. It's enough. It's an inner product space. C contained in X is a convex, closed convex set. Okay. Closed convex subset of H. In particular, a subspace is a closed convex subset. Closed, what is convex is if you have xy in C, then Tx plus 1 minus Ty is also in C for all t between 0 and 1. Okay. T is a number between 0 and 1. It's just you take the line joining x and y, a finite line, then that is also contained in that. So that is what is a convex set. And a subspace in particular is a convex set, convex subset. So we have a convex subset and we have a x in H, okay? Then there exists a y. Okay, shall I call it y? Okay, y in C, such that the distance between them, the norm of x, such that norm of x minus y equal to the distance between x and C, which is equal to infimum of, so let me call it y naught, okay, infimum of y, all y in C, such that norm of x minus y. Okay, the infimum is attained at that point. Okay. Okay. Okay.
Sir, do you mean there exists y not belong to C, not the complex number?
Yeah. C is our C. Right. C is the convex set. Okay. We are not dealing with complex numbers. Yeah. Okay. So we want to choose a y naught such that this happens. Okay. First, what shall I do? So for replacing C by C minus x. Okay. If you have, so if C is a closed convex set, then C minus x, you just translate it. Okay. You move C by x. Okay, which you can do. That's also a closed convex set because addition is continuous, and and you can verify the convexity also. So by replacing this, we assume what? Assume x to be 0. Okay. So that you need not worry about something, some plus sign. Okay. So if you can prove for the convex set C minus x, then you can put same thing is, we are proving for any convex set. Okay. So, if for x there exists a minimal thing, from 0 there exists a minimal distance. Minimum distance is attained for 0, then it is attained for any convex set. Then in particular, for C minus x also it will be attained. So then you can find the minimal distance for C from x. Okay. So without loss of generality, we can assume x equal to 0. That's what I'm saying by replacing C by C minus x. Okay. I think this is okay. 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 So then there exists. So let's assume the minimal distance to be some, call it some alpha d. Let d equal to, so the minimum distance, which is the infimum of y in C, norm of y. Okay, that's right. Because x is 0, so which is just norm of y. Y minus 0 is this. Okay. Okay. Then there exists yn, a sequence contained in C such that yn, norm yn converges to D. See, if you don't assume x equal to C, then yn minus x, all those things we have to consider. This is simpler. So that's why I'm just we are replacing C by C minus x. Okay. So this is what it means. This norm yn will decrease to D. Okay. In particular, it converges to D. Okay. So we want to say that the point is, if you have a Banach space or Hilbert space, if yn converges to some y, then norm yn will converges to norm y. But if norm yn converges to norm y, that need not imply that, it's clear, even in complex number, this is not true. If modulus converges, then the original sequence need not converge. So mod yn converges to D. Okay. Then I want to say that actually yn converges. That's what I want to prove. So for that, I want to do the following. I want to say that yn is a Cauchy sequence. Okay. If I say yn is a Cauchy sequence, then since it will have a limit because it's closed, the I mean, we assume that it's a Hilbert space, okay? So and I said it's inner product space, that's not enough. We need it to be in the inner product. I mean, if it's not Hilbert space, then this will not work. Okay? It is a Hilbert space. Okay. Of course, if you have a non-closed subspace, this will not work, right? So you need it to be Hilbert space. What I said is to define orthogonal complement, you don't need Hilbert space. But so if you want to define, if you want to prove this theorem, then you need Hilbert space, right? So I want to prove that this Yn is actually a Cauchy sequence, okay? Because it's a Hilbert space, and then because it's a Hilbert space, there will exist a limit, and because C is closed, the limit will be in C, and that is the point we need, okay? So for that, I have to consider Yn minus Ym. So let me consider Y minus Z, okay? Y minus Z. So what is that? Y minus Z. I want to say that this is greater than Y minus Z is Y minus Z plus Y plus Z. Okay, let me take this square. Okay, so this is less than or equal to norm Y square plus norm Z square. This is true for anything. Okay, sorry, this is equal to. This is true for any Y and Z. That's right. Okay, right. So
There will be a factor of 2 on the right side.
correct. So I mean, we are going to take something going to 0 anyway. So yeah, there is a factor of 2 on the right side, right? Okay. Now I want to say the following. So suppose Y and Z are in C, okay? Then half times Y plus Z is also in C because it's convex. Sorry, this is C. Okay, right. So this implies norm of Y plus Z square, okay? Which is, I mean, this is in C, so norm of this should be greater than that D, okay? Greater than 4 times D square, right? That is true. So I can write, that inequality will become like this, 2 times norm Y square. So norm Z square is greater than or equal to norm Y minus Z square plus 4D square. Y plus is there. This is right. This is okay?
Yes.
Yeah. Yeah. So this is true. So I have just used the fact that half of times Y plus Z is there. Now I choose let Y equal to Yn. Y is Y and Z equal to Yn. Okay. Right. Then the right hand side converges. I take Y equal to Yn and Z equal to Yn. Right hand side converges to D square, 4D square, right? This is norm Ym square, this is norm Yn square. As N and M goes to infinity, the right hand side will go to 4D square. Okay. So left hand side you have 4D square plus Yn minus Ym. Okay. So this implies from the left hand side. So this implies Yn minus Ym whole square goes to 0. Here left hand side you have 4D square plus something. Okay. This is what we need. Let me come back. Is quotient. So there exists Y naught. See, set that Yn converges to Y naught. And of course, norm Yn square will go to D. And since it's not a handle, goes to D. This distance between 0, norm of Y naught equal to D. That is the distance between 0 and this. This is clear. The yn ym is Cauchy. From this, in this inequality, I substitute y equal to ym and z equal to ym. Okay. Then both this norm, both this whatever we have in the right hand side, that will converge to y naught. That will converge to 0. Sorry, that will converge to d. Okay. So the right hand side will. So sorry, this is left hand side. I always mix right and left. So that is the problem. Yeah, I'm sorry. The left hand side goes to 4d square. Even while driving, if someone says right, I turn the left side. So this is okay. Left hand side goes to 4d square. Norm yn square goes to d square. Norm ym square go to d square. So if I assume y and z are both yn and ym, okay, they will go to d square plus d square, 2 times d square. I mean d square plus d square, 2d square, 2 times 2d square is 4d square. So you get 4d square cancel. Whatever the remaining thing, that should go to 0, which is just ym minus ym whole square. Someone please say okay, then I will go ahead. Is it fine?
Yes, yes.
Yes, sir.
Okay. So this is a Cauchy sequence. So there exists a limit, and that limit has the minimum. On that limit, whatever that vector, the minimum distance is assigned. Okay, that's all. That's what we wanted to prove. So if we have a closed convex set, then for any point, the distance between that set. I mean, if you have a closed set, you can talk about distance. So and the distance is attained at some point. That's what this says. Okay. So now we want to go to orthogonal complement. So what do we want to do? We have defined orthogonal complement, but we will consider subspace now. Okay, this is the next proposition. So H be a Hilbert space. Let us take it to be a Hilbert space. Okay.
So is the y naught we got in the previous theorem, is it unique?
Yeah. Yes. I mean, it's clear, no? It's unique because it will follow from the triangle inequality of the metric. The minimum distance is attained at a point, no? No. Is it unique? You can have. It will follow from the next thing. It's unique for a subspace, but because it's a convex space, it should be. Now, if you have if you have something like this, okay, then you can have a point which is not the minimum distance is not unique, but if you have convex set, it may be unique. For a subspace, it is unique.
Yeah, so it need not be. Yeah.
It need not be unique in general for a set. For a closed set, it need not be unique, of course. It's clear. From if you draw something, you can see that distance can be attained in many places. But a convex set, it may be unique.
In particular, we can consider the ball around X.
What?
In particular, we can consider a closed ball around X.
No, then the distance would be 0, right?
What is ball?
Okay. I mean the boundary of the whatever.
But the boundary is not convex.
No, what is the point? What are you trying to say?
Okay.
No,
Okay,
clear that the point is not unique for an arbitrary set. I'm just trying to see for a convex set, it may be unique. Okay? So suppose if we have two such things, okay, yeah, let us see whether convex set, it may be unique. The point is you have suppose some y naught and z naught equal to R in C, and d of y naught, I mean, so, and yeah, you can have norm of y naught equal to norm of z naught. That's not the point. Then so half of y, so the only thing you have is half of y naught plus z naught is also in C. Okay. So whether it is unique, I'm not sure. Yeah, it should be unique.
So as in from this inequality, 2 times norm y square plus norm z square greater than equal to norm of y minus z square plus 4d square. From this inequality, like if we have 2 points y and z such that the distances are d,
Yeah.
Then if we substitute in this inequality, we get that norm of y minus z less than equal to 0.
Correct. Yeah. So
And that means y equals 0.
yes,
Yeah.
correct. Yeah, you don't have to do this. Yes. You're absolutely right. Very good. That's right. So let us call this inequality star. Okay. Okay. If we have two such things, then you can see that that's right. So something greater than, so we have proved that with the D I have written something. This is not the inequality I want. This inequality. Okay. We have star. Okay. If we have 2 points, suppose y naught and z naught, suppose, yeah, that's what you said. What's your name?
Shayanta.
Okay, Sayantan. So such that both these things satisfy this, norm of y naught equal to norm of z naught. Okay. Then you can substitute in star. That will say that this is d squared, that is d squared. So y minus y naught minus from star. Okay. Suppose we have, then from star implies norm y naught minus z naught equal to 0. Okay. So it follows. So it is unique. So it's unique for a convex set. And we are using convexity crucially. So that's why it's true. Right. Good. Okay. So we have a unique point. Okay. So which we will use now. Okay. So proposition. Proposition or a theorem. I call it a theorem. Sorry. Not comfortable. Okay. So we have a Hilbert space. And let M, what happened? M contained in H be a closed subspace. Okay. Then for any y in H, there exists x in M and x perp in M perp. M perp we have defined. It's just the orthogonal complement which I have defined here. Okay, it's all those vectors which are orthogonal to this. Okay. X perp such that, I mean, just a direct sum. That's what I want to say. Y equal to x plus x perp. For any x, there exists unique x and unique y x perp. So if I say that, okay, this just says that H is the direct sum of M and M perp. Okay. I mean, you can see that M intersection M perp is 0. Okay, notice. So if X is in M, sorry, M intersection M perp, then XX should be equal to 0. Okay, X should be orthogonal to 0. This implies norm X square equals 0. Okay, so X has to be 0. So this just says that we usually, and I'll come to that. So the statement till now, the statement is if you have any y in H, and you have a Hilbert space H, and you have a subspace M, and then for any x in H, any y in H, there exists a x in M and x perp in M perp such that y equal to x plus x perp. You have two orthogonal vectors, okay, such that y equal to x plus. Further, x is the nearest vector of y in M, and x perp is the nearest vector of y in M perp. Okay, so okay, so that's right. So I should have defined earlier. Further, I mean, this is what this says anyway. Further, not further. That's what the statement is. that is H equal to M direct sum M perp. Here I'm using the direct sum, I'm using a circle. That is, this means as algebraically H will look like M direct sum M perp. That's one thing. And M is orthogonal to M perp. Okay. And H equal to M direct sum M perp algebraically. Okay, that's what we have said. M is orthogonal to M perp, of course. And I mean, that's by definition. And we say we say H, some H is M direct sum M perp in Hilbert space language if they are orthogonal. So maybe I should have defined it earlier. Maybe is there a space here? Okay, very good. Definition. H equal to H1 direct sum H2 in Hilbert space language if H1 is orthogonal to H2, okay, and H equal to H1, I mean here H2 algebraically, okay. That is, for any element in H, there exists something in H1 and H2 such that X and Y in H1 and H2 such that Y, I mean, for any Y in H, there exists Y1 in H1, Y2 in H2 such that Y equal to Y1 plus Y2. Okay, so that's what the statement is. And here I am saying that if you have any H and if you have a M, then H looks like M direct sum M perp. That's what the whole thing says. Further, M double perp equal to M itself. Okay, that's all. I mean, the proposition is long, but the proof is not that long. So let Y is in H. Okay, we have M contained in H and Y is in H. Then choose X in M such that which is the nearest distance, such that dy M equal to X minus Y, right? Okay, right. Should I take it from M or should I take it from M perp? M is fine. Okay. Yeah, now this will be in M perp. That's what I want to say. Okay. Now let X minus Y equal to X perp. Okay. Then clearly Y equal to X plus X perp. Okay. I only have to say that, I mean, X is in M and X perp is in M perp. Right. I only have to prove that X perp is in M perp. That's what I want to prove. Okay, so I want to prove that X perp is in M perp. Okay, let me do the following. Norm X perp square equal to, of course, X perp look is equal to X minus Y, right? X minus Y square. This is less than or equal to X minus Y minus some epsilon Z. Z is in M. Okay. Y, X is in M. Maybe if it will be easy if I write it as Y minus X. I mean, I'm writing the same thing. X minus Y, I'm writing it as Y minus X. So here also I should write Y minus X, I'm sorry. I mean, Y equal to X plus X perp. So X perp should be Y minus X, not X minus Y. Okay. And we are decomposing Y. We have a Y in H. We have chosen a X in M, where the shortest distance is attained. Okay. Then we have defined X perp as Y minus X. I want to prove that this X perp is actually, I mean, I have denoted it as X perp. I want to actually say that this X perp is in M perp. That is, X perp is orthogonal to whole of M. That's what I want to say. Okay. So I take any Z, further this is true. right? This is true. This is because this is distance between y and x. Okay, whatever, this is distance between y and x. This is distance between y and x minus epsilon z. But x minus epsilon z is also in m. This is in m. Okay, this is in m. So the distance between y and something is in m will be greater than that because the minimum distance is attained at x, right? So this norm is greater than this. Okay, for every epsilon. Epsilon is something arbitrary greater than 0. Right? This is true. Clear, no? So now I expand this. So this becomes, I don't want to write y minus x. So this y minus x is x per square. Okay, write it like this. Minus 2 real of, this is x per, okay, this is x per, okay, 2 real of x per and z, epsilon z, okay, plus epsilon square times norm z square. Okay, so we have got norm x perp here, norm x perp here on both sides. So this implies I should have taken plus there, or then that will become minus, no? So this is greater than that. That's right. So what should I do now? So I have got minus sign there. So I should only take it that side. This is okay. So this implies 2 times, right, this is okay. Two times real part of x per and epsilon z is less than or equal to epsilon square times norm z square for all epsilon greater than 0. Right? So as epsilon goes to 0, this implies real part of x per, you can cancel one of the epsilons, epsilon, and then this. Okay, this take epsilon goes to 0. This real part of x per z equals 0. Is okay?
Yeah.
Yes, yes.
Okay. Okay, this is true. Z is arbitrary for all z in m. Okay, I have chosen in m, z in m. Okay, so for all z in m. But then since m is a subspace, see if you have, you can take iz for example. Okay, m is a subspace. This implies real of x per iz is also equal to 0. But that is the imaginary part. Okay, so that implies real of x per by taking or considering this by this. This is actually x perp z equal to 0 for all z in m. So this implies x is in m perp. Sorry, x perp is in m perp. Okay. Y equal to x plus x perp, where x is in m and x perp is in m perp. Okay. And this is an algebraic direction, so they have to be unique. Okay. I mean, we can prove it otherwise also. Suppose y equal to some other x prime x prime plus x prime per, okay, with x prime in m and x prime per in n per, then x minus x prime plus x prime per minus x per equals 0. Okay, so this is 0 means, but then for orthogonal element, so if x and y are orthogonal, this is another exercise, okay, not exercise, you can easily see. If x is orthogonal to y, then norm of x plus y square equal to norm x square plus norm y square. Okay, this is the Pythagoras identity. This is just clear. Norm x plus y square equal to norm x square plus norm y square plus 2 times inner product xy. Real part of inner product xy. But inner product xy is 0, so it looks like this. Okay. So this will imply that norm x minus x prime square plus norm y minus y prime square equals 0. Okay. That implies x equal to x prime, y equal to x prime. Okay. If you look at the notes, you may get confused. But this is just the Pythagoras. I'm using Pythagoras identity. Okay. Is okay. So x and y are unique. Otherwise, also we have already proved that m and m perp, their intersection is 0, which we have proved, and that's what this says. Okay. Is fine.
Yeah. Yeah. Okay.
Okay.
Yes.
So by our definition, H is m direct sum m perp. Okay. So we have proved the following. We have chosen a y in H. Then we got a x, which is the nearest point from here. Then we just subtracted it, and we got a x perp in m perp. When we proved that x perp is in m perp. So, and we proved that x and x perp are unique. Okay. Now we only have to prove that x perp is actually the point at a minimum distance from that y, to the original y. That is one thing we have to prove. Then we have to prove that m double perp is m. Okay. So what is m double perp? M perp of perp. So suppose, so let us prove that. Suppose to prove m perp equal to m. So suppose some y naught. So let's take z. We have already y there. Suppose z is in m perp, which is m perp. Okay. Then there exists x in m and y in m perp, such that z is equal to x plus y. Okay. Maybe I call it x perp. Okay. But m is orthogonal to m perp. Okay. So m is contained in m perp. Okay. By definition, m double perp. So now z is also in m double perp, x is also in double perp. So z minus x is in m double perp. Okay. So that is x perp is also in m double perp, which is equal to z minus x, right? Okay. And it's also in m perp. So something is in m perp and n double perp. This implies x perp has to be 0. Okay. So z is equal to x which is in m. So if we have some z is in m double perp, then that is in m. That's what we have proved. So m double perp is equal to m. Okay. Is fine?
Yes.
Okay. So if somebody is no for somebody, please ask me. And not just here, from anywhere. Okay. So now this proves that. This proves what? Yeah. Now you can work with, now this is m. So now you can start with y and find the nearest point in x perp, which is some point. Then you will get a sum x, and then you can write the decomposition. But the decomposition is unique. Okay. Now, I mean, this is decomposition y from x plus x perp is unique. Now we have already proved, we have chosen this x to be, I mean, we have chosen this x and that is a unique point. There is no other point. Okay. Now this x is a unique point from m. Unique point, I mean, x is the nearest point from m to y. Okay. This x perp has to be the nearest point from m perp to y. Because we can start from m perp. From y, we can start from m perp. Choose a point x perp. Choose some point x perp. Then that has to be this point because it's unique. then you get a x which is orthogonal to this. Okay, we can go around that. The argument is clear.
Yes, yes.
Okay,
So we are starting the other way, right?
exactly, by replacing. I mean, this is because we have proved m per perp equal to m. Okay, then we will get something in m per perp that is equal to m. Okay, I assumed m is closed. Okay, that's very important. Yeah, did I assume there? Yeah, closed subspace. I mean, this is true only if it is closed subspace. By replacing m by m perp in the above argument, okay, we get x perp is the nearest point in m perp to y. Okay, so we have proved everything in this theorem. Okay, so if we have a y in h, then we get x and x perp in the m and m perp, such that the x is the nearest point from m, x perp is the nearest from domain, such that y equal to x plus y. And we also proved that m double perp equal to m. Okay. Now there is one small corollary which is clear. If m is contained in h, then m double perp equal to m. Now this is let me write the difference. We can say something more. If S is any set, S is contained in H, okay, any set, then for any set, S perp is a closed subspace. It is subspace is clear because inner product is linear. Subspace follows because inner product is linear. Okay. If x is orthogonal, then alpha times x is also orthogonal. If x and y are orthogonal, x plus y is orthogonal because inner product is linear. Closeness follows because inner product is continuous. Okay. So this is exercise. Okay, let me just do it. Inner product is continuous, you want to find. So that is just if xn minus x, yn minus y. There is no exercise, I'm just doing it. Less than or equal to norm xn minus x times norm yn minus y. We have already proved norm is continuous. So if xn converges to x, yn converges to x, then this will go to 0. So inner product is continuous as a two variable function. Okay. So because inner product is continuous, if xn is a sequence which is orthogonal to some subspace, then the limit is also orthogonal because inner product is continuous. So because of that, S perp is a closed subspace. Okay. Then S perp, which is a closed subspace, and S double perp, which is also a closed subspace, equal to span closure of S. Okay. You can see, so proof, maybe proof. Proof of not the exercise, proof of the corollary. So clearly, span closure of S is contained in S double perp. Okay. I mean, if S is orthogonal, then you take the span of that. This is also orthogonal to it. Then the closure. That's what we have said. I mean, that's the argument we have used, using inner product linearity and orthogonality of inner product. Clearly, span is contained in S. If some S is orthogonal to S perp, okay, you take the span of S, that is also orthogonal to S perp. Okay, so this is all contained in S double perp. Okay, then the closure is also contained in double perp. We have to prove the other way only. Okay. Okay, so to prove the other way, S double perp is contained in S perp. So suppose X is orthogonal to S perp. Okay. Suppose X is orthogonal to X perp, this perp, then it should be in the span closure of that. What's the time? It's 20. So I will finish with this. I should do this. I want to prove that yes, double perp is contained and span is closure. Okay. Span is a vector space. So we just have to do some yes. This is just this. Okay. You take yes triple perp. I mean, this is true. Okay. So we have span this contained in this. Okay. For closed subspace, we have already proved that yes, double perp is equal to that. Okay. So span, yes, closure perp. Okay. Which is a closed subspace, which is equal to see when you take perp, the inequality will be reversed. What do you have to show? I want to prove that we have this. This is clear because if we take some set, then they take this close. That's also will be orthogonal to this. Okay, and we have to prove that yes, double triple perp. Okay, this is it's the other way. It's contained in span closure S perp. Okay, now this is equal to S perp. Now this is equal to S double S.
Sir,
Yeah. This is just clear. You take the orthogonal complement. Yeah. Say it
sir.
again.
So span S closure is a closed subspace, right?
Correct. Right.
So we can take that to be M.
Yeah, that is equal
and,
to take the double perp. Yeah, you will get that. Yeah.
And for any vector in S perp, we can write it as y plus z, where y is in M and where M is span S closure,
That's,
and Z is in the span M perpendicular.
yeah. So you are going through the proof, same proof like earlier.
Yes, sir.
But I just want to get it as I'm just getting confused unnecessarily. By taking double perp. See, the point is if you have some M1 is contained in M2, okay, then M2 perp will be contained in M1 perp. I just want to use that and get it immediately. That's all.
But then if we reverse it, then again we'll get the same thing. So
if you reverse it, you get S perp is contained. The perp of this is S perp is contained.
No,
in,
sir. No, sir. What I mean is we take any vector x in S perp, and
because it's a closed thing, you can write it as something here and something plus something there.
yes, and because and because span S closure is contained in S perp, then the difference is also contained in S perp, and that is orthogonal to the S perp. So we can prove this thing.
You are absolutely right. That is the previous proof, which I have already done. I just want to state it as a general observation by this. Okay, I'm sure this will follow from that. I leave it as an exercise.
So we can take S is contained in span as closure and then apply perpendicular twice and use this equation to get it.
Yeah, this equation. Yeah, I'm sure you will get it from this. Okay. Okay. I will end. If you don't get it, you
Sir, are we having classes in the next week?
yeah. So you people may not attend. You can watch the video. We cannot afford to cancel the class, 2 classes next week. Okay, we don't have that much time.
At the same time, 5 p.m.
Yeah, same 5 p.m. Maybe after exam you can come after 15. Maybe if you want later, I can make it later, 5:30 or something. After the exam, if you want to sit, if you don't mind. Do you want it?
I mean, my exam is supposed to end by 4:30 or something like that. So I guess it isn't necessary.
Okay. So 5:15 I will start. Okay.
Yeah, that would be
15
best.
to
Yeah,
6:30 we will have the class. Okay.
yeah.
Okay then. Bye.